Let's get one thing straight before anything else. The headline promising this happened 2 minutes ago is wrong, and I want to tell you exactly why, because the real timeline actually makes this story better, not worse. The moment being described here, the James Webb Space Telescope capturing its first ever direct image resulting in the discovery of a brand new world, happened on June 25th, 2025, published in the journal Nature, and it's now sitting quietly in NASA's own official exoplanet catalog as one of the confirmed entries in humanity's growing census of worlds beyond our solar system. That's not 2 minutes ago. That's over a year of follow-up observation, confirmation, and scientific scrutiny standing behind it. And that's exactly why it's worth understanding properly right now. Because what looked like a faint, uncertain smudge of infrared light back in the summer of 2025 has since held up, been checked, cross-referenced, and added to the permanent scientific record. Think about what that actually means for a moment, because it's easy to skim past. A claim that gets rushed out, unverified, the instant it happens, and a claim that survives a full year of independent scientists trying to poke holes in it before it earns a permanent spot in NASA's own database, are not the same category of information, even if they end up describing the exact same underlying discovery. The first is a rumor with a countdown clock attached. The second is science that's actually been tested. This particular discovery belongs firmly in the second category, and that's worth knowing before we go any further. Let's go through exactly what Webb actually found, why it took a telescope worth $10 billion years of preparation just to catch a single point of light, and what's happened with this discovery and with the broader hunt for imaged worlds in the year since. Start with why this was ever considered a first at all, because Webb had already been operating for nearly 3 years by the time this happened, and it had already photographed plenty of exoplanets before this specific announcement. The distinction matters. Since Webb came online in 2022, its most common use for exoplanet science has been studying worlds astronomers already knew existed, confirming their presence and analyzing their atmospheres using a technique called transit spectroscopy, watching the tiny dimming of a star's light as a known planet passes in front of it, then reading the chemical fingerprint of whatever atmosphere that starlight passed through on the way to Webb's mirrors. That's an incredibly powerful technique, and it's how Webb identified carbon dioxide in an exoplanet's atmosphere for the first time back in August of 2022, one of its earliest major science results, a detection that itself required the telescope to measure changes in starlight amounting to a dip of only a few parts in 10,000 as the planet passed in front of its star, an extraordinarily delicate measurement in its own right. That kind of atmospheric fingerprinting has since been repeated on dozens of other known worlds, steadily building up a genuine catalog of what different exoplanet atmospheres are actually made of: water vapor, methane, sulfur dioxide, even signs of clouds and hazes on planets light years away. But it's fundamentally a technique for studying planets you already know are there, detected first through some other method, most commonly the regular, repeating dimming pattern a transiting planet produces as it repeatedly crosses in front of its star from Earth's point of view. Direct imaging, actually seeing a planet as a distinct point of light in a photograph, separate from the glare of its host star, is a completely different challenge, and it's the technique this particular story is actually about. Here's why direct imaging is so brutally difficult in the first place. A star is typically millions or billions of times brighter than any planet orbiting it, and from the distance of another star system, the angular separation between a planet and its star, as seen from Earth, can be smaller than the width of a coin held miles away. Trying to see the planet directly means trying to spot an incredibly faint point of light sitting immediately next to an overwhelmingly bright one, roughly equivalent to trying to photograph a firefly hovering directly beside a lighthouse beam from several kilometers away. Webb tackles this problem using 2 main tools: coronagraphs, small masks built directly into some of its instruments that physically block out the bulk of a star's light before it can overwhelm the detector, and its mid-infrared instrument, known as MIRI, which is specifically tuned to detect the kind of heat signature a young, still cooling planet gives off, since planets that have recently formed retain leftover heat from their own formation and glow relatively brightly in infrared wavelengths, even when they're too faint to see clearly in ordinary visible light. Webb's very first direct exoplanet image, back in September 2022, used exactly this approach on a planet called HIP 65426b, already known gas giant between 6 and 12 times the mass of Jupiter, sitting about 385 light-years away, chosen specifically as a kind of demonstration target to prove Webb's coronagraphs actually worked as designed. Sasha Hinckley, the astronomer at the University of Exeter who led that observation, called it a transformative moment for the telescope, and it genuinely was, showing off exactly how cleanly Webb's instruments could suppress a star's glare. But HIP 65426b was already a known planet. Webb was simply confirming it could see something astronomers had already found using other methods. What happened in June of 2025 was different in one crucial way. It was new. The target was a young star called TWA-7, sometimes also referred to by its other designation, CE Antliae, sitting roughly 111 light-years from Earth in the southern constellation Antlia. TWA-7 is what astronomers call a T Tauri star, an extremely young star, only about 6. 4 million years old, still surrounded by a wide, sprawling disk of leftover debris, gas and dust that never fully condensed into planets. The same kind of raw material our own solar system's planets originally formed from billions of years ago. That debris disk isn't a smooth, uniform ring either. Earlier observations had already revealed it was structured into 3 distinct concentric rings, separated by visible gaps. And gaps like that are exactly the kind of feature astronomers have long suspected are carved out by the gravitational influence of a planet still in the process of forming, quietly clearing a lane through the surrounding material, the same way Earth's own gravity keeps its orbital path clear of debris today. Using Webb's MIRI instrument and its coronagraph, a research team led by astronomer Anne-Marie Lagrange at the Paris Observatory pointed the telescope directly at that gap and found something. A faint, distinct source of infrared light, sitting almost exactly where a planet massing around a third of Jupiter's mass, roughly comparable to Saturn, would be expected to sit if it were the object responsible for carving that particular gap in the debris disk. Its estimated temperature came out to around 120 degrees Fahrenheit, cool enough, in fact, to make it one of the coldest exoplanets ever directly imaged at the time, a genuine testament to just how sensitive Webb's infrared detectors actually are, since a target that faint and that cool would have been essentially invisible to any space telescope built before it. Lagrange and her team were careful, in their own published statement, to note that the object's brightness, its color, its distance from the star, and its exact position within the gap were all consistent with a young, cold, Saturn-mass planet actively sculpting the structure of the surrounding debris disk, exactly where a planet of that mass would be predicted to sit. It's worth being honest about the uncertainty that existed at the moment of that initial announcement, because that's part of what makes the follow-up story worth telling. The research team calculated there was roughly a 34% chance that the object they'd photographed was actually an unrelated background galaxy happening to sit at almost exactly the right spot in the image by pure coincidence, rather than a genuine planet. That's a small chance, but it wasn't zero, and reputable outlets covering the discovery at the time, including the BBC's Sky at Night magazine and Sky and Telescope, were careful to describe it as not yet confirmed, a strong candidate rather than an ironclad certainty. That kind of careful hedging is exactly what responsible science reporting is supposed to look like in the moment right after a genuinely new result comes in, before independent teams have had the chance to double-check it. So what's actually happened in the time since, because that's the part that turns this from a promising 2025 announcement into a settled piece of the scientific record. As of NASA's own exoplanet catalog, maintained by the California Institute of Technology under contract with NASA's Exoplanet Exploration Program, TWA-7, B now appears as a listed catalog planet, described plainly as a gas giant with roughly a third of Jupiter's mass, orbiting its star at a distance of about 52 astronomical units, taking a little over 553 years to complete a single orbit. That listing represents the object graduating from an exciting but tentative candidate into the kind of confirmed, cataloged entry that becomes part of humanity's permanent working census of worlds beyond our own solar system, sitting today alongside the roughly 6,000 other exoplanets confirmed through every detection method combined. Transits, radial velocity wobbles, gravitational microlensing, and now, in this specific and still comparatively rare case, direct imaging itself. It's worth understanding this against the full sweep of direct imaging history, because that history is short enough to walk through entirely, and it puts TWA-7b's place in it into sharp focus. The very first exoplanet ever directly photographed by any telescope was captured in April 2004, not by Webb, which didn't exist yet, but by the Very Large Telescope in Chile, using an instrument called NACO in an observation led by astronomer Gail Chauvin. The object, later named 2M7b, turned out to be a massive gas giant roughly 5 times the mass of Jupiter, orbiting not an ordinary star, but a brown dwarf, a kind of failed star too massive to be a planet, but not massive enough to sustain the nuclear fusion that powers true stars, sitting about 230 light-years away in the constellation Hydra. Anne-Marie Lagrange, the very same astronomer who would go on to lead the TWA-7b discovery team 21 years afterward, was actually a member of that original 2004 European team as well, describing the 2M7b result at the time as a first step toward one of the central goals of modern astrophysics, eventually characterizing the composition of planets down to something resembling our own Earth. The next major leap came in 2008, when 2 independent research teams, one led by Christian Marois and another by Bruce McIntosh, used the Keck and Gemini telescopes to photograph not just one planet, but three, all orbiting the same young bright star, HR 8799, roughly 129 light-years away, with a fourth planet in the same system confirmed shortly afterward. That family portrait of an entire multi-planet system, imaged directly rather than inferred, became one of the most closely studied targets in the entire field, a genuine benchmark. Other observations are still compared against today. From there, progress came in increments, each new imaged planet chipping away a little further at the minimum mass and minimum temperature astronomers could successfully detect this way. About a decade after HR 8799, researchers directly imaged a planet called 51 Eridani b, roughly twice the mass of Jupiter, at the time the smallest and coldest planet ever captured using this technique. Even with all of that steady, hard-won progress, by the time Webb launched in December 2021, the total number of exoplanets ever confirmed through direct imaging across every telescope on Earth and in orbit combined stood at only around 50, a tiny fraction of the nearly 6,000 exoplanets known through every detection method put together. That's the real backdrop TWA 7b's discovery landed against: 21 years of incremental, hard-fought progress, moving from a 5 Jupiter-mass gas giant around a failed star in 2004 down to a third of a Jupiter-mass planet around an ordinary young star in 2025. Each step representing years of instrument refinement, rather than any single dramatic breakthrough. The overwhelming majority of the nearly 6,000 confirmed exoplanets known today were found indirectly, most commonly by watching the tiny, repeating dip in a star's brightness as a planet passes in front of it from our point of view, a method that tells you a planet exists and roughly how big it is without ever actually producing a picture of the thing itself. Direct imaging, actually capturing photons that bounced off, or in this case radiated from, the planet's own body, remains one of the rarest and most technically demanding detection methods in the entire field, precisely because of the firefly beside a lighthouse problem described earlier. TWA 7b's confirmation meant it joined a genuinely exclusive list of planets humanity has ever actually photographed directly, rather than merely inferred through their gravitational or optical effects on a distant star. It's worth explaining why a gap in a debris disk is treated as such compelling evidence for a hidden planet in the first place, because it's not just a visual coincidence, it's grounded in fairly straightforward orbital physics. A young star's debris disk is made up of countless small particles, dust and rubble left over from planet formation, all loosely orbiting the star. If a planet is embedded within that disk, its gravity will steadily clear out a lane along its own orbital path, pulling nearby material either into itself or flinging it into different orbits entirely, in essentially the same way Jupiter's gravity has carved a set of well-known gaps into the asteroid belt in our own solar system. Regions where an asteroid's orbit would be so repeatedly disturbed by Jupiter's gravity that virtually nothing remains there today. When astronomers see a similarly clean, well-defined gap in a young star's disk, positioned at a distance and width consistent with a planet of a particular estimated mass, it becomes a strong, physically motivated prediction for exactly where a hidden planet ought to be sitting, well before anyone actually manages to photograph it directly. TWA7's disk had already shown this kind of structure, 3 distinct rings with clear gaps between them well before Webb's 2025 observation, meaning astronomers already had a specific, physically justified target zone to search when they eventually pointed MIRI's coronagraph at exactly the right spot, and the eventual detection landing precisely inside the predicted gap, rather than somewhere else in the image entirely, was itself a meaningful piece of supporting evidence, not merely a lucky coincidence. Webb's coronagraph, the physical hardware doing the heavy lifting throughout all of this, is worth explaining a little further too. Rather than being a single simple shutter, it's closer to a carefully engineered occulting mask built directly into instruments like MIRI, positioned precisely to block the concentrated core of a star's light, while still allowing the comparatively much fainter light from anything orbiting nearby to pass through largely undisturbed, combined with careful image processing that subtracts out any remaining scattered starlight and background noise. This is what allows something as faint as a cold, Saturn-mass planet, radiating only the leftover heat of its own formation, to actually show up as a distinct, measurable point of light in the final processed image, rather than being completely swallowed by its star's overwhelming glare. Sasha Hinckley's comment back in 2022, after Webb's very first coronagraph demonstration on HIP 65426b, that it was really impressive how well the instrument suppressed the host star's light, was effectively astronomers confirming, for the first time with this specific telescope, that the tool built to do exactly what happened 3 years later with TWA-7b actually performed as well in practice as it had on paper. There's also a broader, ongoing story worth folding in here because the year since TWA-7b's announcement has actually been a busy one for direct exoplanet imaging generally, And understanding that context helps explain why this specific discovery mattered as more than an isolated headline. In May of 2026, NASA scientists released new images of a previously known exoplanet called HIP 65426b, the same gas giant Webb first photographed back in 2022 during its original coronagraph demonstration, this time using an expanded range of instruments to gather considerably more detailed data than the original proof-of-concept images had captured. Around the same period, a separate Webb team achieved something genuinely new in its own right, directly analyzing the surface, rather than the atmosphere, of a rocky exoplanet called LHS 38444b, a so-called super-Earth, roughly 30% larger than our own planet, located about 50 light-years away. That observation, described by the researchers involved as revealing a dark, hot, barren rock, marked the first time Webb had ever directly studied the actual solid surface of a planet beyond our solar system, rather than an atmosphere or a point of reflected or emitted light, comparing its properties to airless, heavily cratered worlds in our own solar system like Mercury. Together, these threads show a telescope steadily working through a genuine progression, first proving it could photograph a known giant planet at all, then discovering an entirely new one for the first time, then pushing on to characterize surfaces and atmospheres in ever finer detail, each step building directly on techniques proven in the step before it. It's worth explaining, too, why a discovery like TWA-7b matters beyond simply adding one more entry to an already crowded catalog of known worlds. Every previous giant planet directly imaged by any telescope, going all the way back to the first such image in 2004, has been a relatively massive, relatively young, and relatively hot object, because those are precisely the characteristics that make a planet easiest to spot against the glare of its star using current instruments. TWA-7b's mass, at roughly a third of Jupiter's, made it, at the time of its announcement, the lowest mass planet ever confirmed through direct imaging, a genuinely meaningful technical milestone rather than just a publicity-friendly superlative. Every incremental drop in the minimum mass astronomers can successfully image directly represents real, hard-won progress in coronagraph technology and infrared sensitivity, and each such drop brings the field measurably closer to a longer-term, genuinely ambitious goal much of the exoplanet research community has been working toward for years, eventually directly imaging planets small enough, cool enough, and close enough to their star's habitable zone to plausibly resemble Earth itself, rather than the hot, young gas giants that have dominated this particular observational technique since its inception. That goal remains a considerable distance away. An Earth-sized, Earth-temperature planet is astronomically fainter and colder than anything imaged directly so far, and current instruments, even Webb's remarkably capable coronagraphs, aren't yet sensitive enough to pull that kind of signal cleanly out of a host star's glare at habitable zone distances. But TWA-7b represents a real measured step in exactly that direction, proof that the underlying technique, faint infrared detection paired with aggressive starlight suppression, can now reach down to planets nearly 3 times lighter than anything imaged this way before it, using a telescope that will keep operating and keep improving its observational techniques for years to come. It's worth being upfront, too, about where the field is actually headed next, because TWA-7b isn't the end of this particular story. It's a milestone inside a much longer one. Multiple next-generation instruments currently in development are being built specifically to push direct imaging further than Webb's coronagraphs can manage alone. Ground-based observatories, like the extremely large telescope, currently under construction in Chile with a primary mirror roughly 39 meters across, dwarfing anything currently in operation, are being designed partly with exactly this kind of high-contrast imaging in mind, aiming to resolve planets closer to their stars and fainter in brightness than what's achievable today. NASA has also discussed future concepts, sometimes referred to under names like the Habitable Worlds Observatory, explicitly built around the long-term goal of directly imaging Earth-sized planets in the habitable zones of nearby sun-like stars. A mission that would take the specific line of progress running from 2M1207b in 2004 through HR 8799 in 2008 through TWA-7b in 2025, and extended all the way to the kind of planet actually capable, in principle, of hosting life as we understand it. None of that exists yet. All of it depends on lessons learned from exactly the kind of incremental, unglamorous, decades-long engineering progress this whole story has actually been about. Coronagraphs, a little better than the last generation. Infrared detectors, a little more sensitive. Image processing techniques, a little more capable of teasing a faint planet's signal out from underneath its star's overwhelming glare. It's also worth sitting for a moment with what TWA-7b actually represents on a more human level, separate from the technical milestones. A star 111 light-years away means the infrared light Webb actually detected left that system around the year the printing press was still a fairly new invention in Europe. traveling silently across the galaxy for over a century before finally landing on a mirror built by humans specifically to catch it. The planet itself, a cold, young gas giant quietly sculpting the debris disk of its own still-forming solar system, has almost certainly existed, doing exactly that, for millions of years, before anyone on Earth ever pointed an instrument its way. What changed in June of 2025 wasn't anything about the planet itself. What changed was that, for the first time, a piece of technology built by our species became sensitive enough to actually catch the faint, cold light that world had been quietly giving off the entire time, turning a hypothetical entry in a model of how planets carve gaps into debris disks into an actual confirmed, photographed object, sitting in NASA's permanent scientific record. There's a satisfying thread running quietly underneath this whole story, too, easy to miss unless you're looking for it directly. Anne-Marie Lagrange, the astronomer who led the TWA-7b discovery team in 2025, wasn't a newcomer to this field, suddenly getting lucky with a powerful new telescope. She had been part of the original European team that captured 2M1207b, the very first exoplanet ever directly imaged, back in 2004, and she spent the following 2 decades working steadily through exactly the kind of incremental technical progress that eventually made TWA-7b's detection possible. That's not a coincidence worth glossing over. It's a fairly direct illustration of how this entire field actually advances, not through sudden, isolated flashes of luck, but through specific researchers spending entire careers refining a single, extraordinarily difficult observational technique, one faint point of light at a time, until a discovery like TWA-7b becomes not a fluke, but the natural next step in a process they'd been pushing forward the whole time. So, to bring this back around to the actual headline that presumably brought you here, did the James Webb Space Telescope just announce the first real image of another world 2 minutes ago? No, and it's worth being straightforward about that rather than pretending the timeline lines up. Did the James Webb Space Telescope capture the first real, genuinely new direct image discovery of an exoplanet in its operational history? A discovery that has since held up under scrutiny and now sits confirmed in NASA's own official catalog of known worlds? Yes, absolutely. And that event, TWA-7b, a cold Saturn mass planet caught in the act of sculpting a young star's debris disk 111 light-years away, remains one of the more quietly remarkable achievements in the telescope's entire operating history. A genuine technical breakthrough in humanity's ongoing incremental effort to actually see the planets scattered across our galaxy, rather than merely infer that they're there. If you found this useful, that's your reminder that a real scientific milestone doesn't need a fake countdown clock to be worth caring about a full year after it actually happened. Follow along for more of these because the hunt for directly imaged worlds is still very much ongoing, with Webb continuing to push towards smaller, cooler, and more Earth-like targets with every passing year. And whenever the next genuine breakthrough in that hunt actually lands, we'll be here to walk you through exactly what it shows, straight from the published research, not from whichever countdown clock travels the fastest online.